Part I didn't cover was about single trajectory diagnostics for mixing. The reason for these is that we have a lot of data in situations in which the full velocity, from situations where the full velocity field is not available, but we have individual tracer trajectories available. The most prominent example of that in my mind is the ocean. We have a huge drifter array database, which is being constantly developed and maintained. I took a snapshot of the global drifter project or drifter array project. I think you can see the date there, April 5th last year, because I was working on something and I needed it, but you can go anytime, go to this GDP data set. It's a wonderful thing. It shows you the current locations and even nationalities, national origins of these drifters in the ocean. Now, this looks like a lot of drifters, right? But if you think about it, and given the size of the ocean, this is a very sparse data set. And if you would like to still infer the existence of barriers in the ocean, and you would like to use the diagnostics that I have described, you would be up for a major challenge, because those diagnostics use a differentiation of trajectories with respect to their initial condition. And when the trajectories are so small, sparse, finite differencing will make absolutely no sense for those, right? So a major challenge is that the drifter data is sparse, and also the drifter trajectories have variable lengths because they were put in the water at different times, and they might stop functioning and will stop functioning at different times. And another challenge from my perspective, hopefully I managed to not necessarily convince, but at least managed to make you think about objectivity as a litmus test or fundamental requirement for any material coherence structure. If you buy into that, and I certainly do, then you find it sort of disturbing that none of the features of single trajectory data, none of the features of trajectory data are objective. And you could go like, wow, hey, I have some ideas and you haven't even heard of those. How would you know that those are not objective? And yet I'm repeating the claim. There's no feature of a single trajectory, even though it's material, that's objective. And that sounds like a very strong statement, right? And I'm repeating that to invite criticism, but I immediately have a proof for you. Just take the observer change that travels, just a shift, don't even rotate. Just pick an observer that travels with that particular trajectory, okay? In the frame of that observer, the trajectory is just a fixed point that doesn't ever move, a single fixed point, okay? So for that reason, any feature of that trajectory, whatever it had, looping number, velocity, angular velocity, whichever way you have this, it's lost, because in that frame, it's just a fixed point. It's not moving anywhere. It's not making any patterns. It doesn't have any particular feature. So that should tell you that whatever feature you're interested in will depend on the observer frame when you're talking about single trajectories. And that's challenge number 2, the sparsity and whatever feature you have is non-objective. So that forced us to basically say, look, we just want to dip into this huge database and work with whatever we have. We probably have to give up objectivity as we know it in its classical sense. But can we at least, weaken it and still uphold some reasonable sense of objectivity, and then divide or derive diagnostics from single trajectories that are giving us meaningful answers? So the idea was, we settled on this term before, after some iterations. We call these diagnostics adiabatically quasi-objective. Wow, that's a lot of words there, but we need all of them. So we came up with this idea of adiabatically quasi-objective diagnostics. In words, it means adiabatic usually refers to some slow variation. So the adiabatic in this context means that we give up indifference to all observers. We give that up, and we will basically require indifference to geophysical observers in the sense that the frame changes that we allow for will be slowly varying, okay? So not so some sort of crazy rotation, but say things comparable to the rotation speed of the Earth, things like that. Okay, so that's the adiabatic, that's what that's referring to. And quasi-objective means that we will call something quasi-objective if in frames that satisfy a certain condition that we can a priori write down, okay? In such frames, this particular field will approximate an objective quantity. Okay, so two things: approximate, and B, only in frames that are qualifying and satisfy certain conditions. So first, and even those then, we will only ask this question, are we getting the same if the frames are related to slow change? You could ask, this is a compromise. You could say it's a compromise, it's not objectivity, and you're absolutely right. But also we wanted to be pragmatic and say, look, this is what we have. We have a huge database. It has a fundamental limitation. Can we at least get something arguably meaningful out of it by giving up some of the generality that we have been working in, but still preserving a meaningful level of generality and mathematical relevance and rigor? Okay, so very quickly, this is the paper, Quasi-Objective Coherent Structure Diagnostics from Signal Trajectories. It came out in Chaos last year. You can find examples there, and we derived such adiabatically quasi-objective LCS diagnostics. Once again, these in qualifying frames, these approximate true bona fide objective diagnostics. However, when you check their framing indifference, you're only allowed to make slowly varying coordinate changes. Okay, so there's one which is sort of the analog of FTLE. We call it a trajectory stretching exponent, or TSE. Here's the frame qualification up here, that it's only true, but it's only relevant in a frame if local accelerations of the trajectories are larger in order of magnitude than the local rate of change of the velocity field. Okay, so we tried this on geophysical data sets. Intuitively, you can imagine that this is pretty much true on average. So basically, a local acceleration that you measure for a trajectory is largely coming from the convective term and not from the rate of change of the velocity field, because the velocity field, whatever you mean by local velocity field, clearly that's a question, but whatever you mean and define it there is slowly varying with respect to the speed of the trajectory. Under that condition and under adiabatically related frames, this TSC, the trajectory stretching exponent, which is basically the trajectory velocity at some time Tn, which is given to you, that's the trajectory velocity you can calculate if you have a trajectory, right? You just differentiate it in time and you divide it by the initial velocity, take the log of that. That's like a directional approximation in a particular direction of the FTLE between T0 and Tn. But it actually turns out to have better, it's better to have some more intermediate information. This is another quantity that also approximates an objective stretching measure, but it's more detailed. It doesn't forget intermediate stretching events. And what it does, it always just checks the same thing, but incrementally between adjacent trajectory velocities, takes the norm of that and sums them up and again normalizes them. And each has different uses, so we discussed that in the paper, but both are quasi-objective LCS diagnostics. What about things like the PRA, for instance, which is, which is for elliptic LCS as well? There's an analog of that too. We call it the trajectory angular velocity. The conditions under which this approximates an objective measure of material rotation is first the same as before. So the acceleration of the tracer must dominate the local rate of change of the velocity. And there's this funny condition, which basically says that, let's start with the right-hand side. What it means is the rate of change of the direction of the trajectory, right? Because we normalize the length of the velocity and look at the rate of change of that. That should be much faster, which this is a measure of rotation, local rotation, the rate of change of the unit normalized velocity, right? That's why this is a rotational measure. It's basically how fast the direction of the trajectory changes. That should dominate another rotation, which you get by this omega t. We've seen what this omega bar means, is the spatial average over the domain of interest of the vorticity. That's what it is. And cross that with that unit vector. So basically you look at the effect of how much vorticity is spinning your local trajectory vector, tangent vector. This would be the measure of that. And compare that to how much, I mean, this is an obviously this is an abstract notion. It's not the average vorticity that's spinning your trajectory, but pretend that that was a material vector. And this is by how much vorticity, this is the angular velocity that it would attain or speed, and compare that to the actual rotational speed of that vector. Okay, and again, there should be an order of magnitude difference. Now, these are things that you can verify offline on models. Obviously, you cannot verify them from trajectory data because you don't have the velocity. But if you have theories or you have models, you have velocity data from a particular region, and you find that these assumptions are okay for that ocean region in general, then are these diagnostics applicable, and they are quasi-objective. Now, in that case, when these two conditions are satisfied, the trajectory rotation average is this quantity, which you're basically summing up individual little measures of rotation. These are the cosine of an inner product in which you're dotting the previous velocity with the current velocity, or the current velocity with the next velocity, but you're also normalizing it by the norm of these. So basically that just gives you the cosine of an angle, so to speak, except that this is calculated from, well, it's the angle between velocities. Then you take the inverse cosine of that translates to an angle, and then you average that angle. So that's why this is a trajectory rotation average, because this is basically the average rate at which things are rotating as measured from the velocity vector. So the history of this is that we came up with this paper and we didn't get it right for the first time. We didn't have all the assumptions in place. Notably, we missed the quasi objectivity. That was one thing that we missed. So the formulas in an erratum that just is coming up soon, this is the last reference, are all the same, but the conditions under which these can be proven to be quasi-objective are not the same. And we're grateful to a group of people who pointed this out. They just published a paper on the archive in which they showed with a counterexample that under the current set of conditions, they could show that these were not quasi-objective. So I want to give credit and thanks to them, Theiser, Friederici, and Günther, and you can find it on the archive, their paper, right? So that prompted us to go back and then see what assumptions we need to make it right. So the formulas are the same as in the paper, but we had to refine the assumptions. If you run this on data, first we ran it on Aviso data because there we could verify the assumptions explicitly because we have the velocities. What you have here is a satellite velocimetry, and we ran this. This is, I don't know how well you can read this. This is the TRA, this trajectory rotation average, or whatever. I think we had different acronyms, different meanings for the acronyms, but the same acronym, from 0 to unit 25 at full resolution. So basically we released drifters from a grid of size 250, 250, and ran this diagnostic on it. It gave fairly good results, but this is a dense set of trajectories. This is not what it was intended for originally. For comparison, we ran relative dispersion as well. Interestingly, the pictures are related, but dispersion wasn't doing all that great. I thought it would give an identical result, but it wasn't. But we also ran PRA, which is okay to do in 2 dimensions, and those PRA actually give a more detailed result, a better result than the trajectory rotation average. But PRA, uses the ability to differentiate individual trajectories, whereas TRA doesn't. TRA, this trajectory rotation average that I showed you, is computed on individual trajectories. It doesn't matter what the resolution of your grid is, it will always give the same result on individual trajectories, always. Whereas these other diagnostics, dispersion, relative dispersion, and PRA, they always depend on who's near you and how far they are from you, right? So if you change the set of trajectories, they will change as well. So that's what we did. We downsampled the set of trajectories from 100 to 10%. This is a factor of 10. And you see, the TRA is pretty robust. And part of the reason is that just because you downsample the trajectory, the diagnostic doesn't change because it only depends on individual trajectories. And the ones you're keeping are just the same as they were before. But dispersion takes a major hit. Just look at that, the same region. PRA is holding up actually pretty well, but it's also, getting fuzzy. Then you downsample to 1%, and these downsamplings are random. So we just basically throw out whatever 90% of the trajectories and keep a few randomly. And again, TRA is surprisingly robust and captures the same feature. Dispersion is becoming a mess, really, and so is PRA. It's very pixelated. At this point, it really, finite differencing is not justified anymore. And finally, we went up to 0.1%, and we're still getting the ghosts of these structures. And again, the individual values at those points, so the TRA is the same. But look at, dispersion and and PRA. They don't indicate any structures. So this was pretty convincing. And then based on that, there was a more recent preprint by my student, Alex Encinas Bartos, who applied this to the real thing, which is this global drifter project data set. So these are actual drifters from that data set. And I think he was using, let's count, 1, 2, 3, 4, 5, 6 in this picture, very sparse. You can read it off from the longitudes and latitudes. And he calculated the TRA in these and basically had a criterion, then extended the TRA, extrapolated and interpolated the TRA over this whole region. Okay, even they only calculated it from these trajectories, and had a criterion that he looked for the outermost convex level curve of that, mimicking the elliptic LCS definition that we had from PRA and LAVD. And that's the vortex boundary he gets from that, just from these 7 trajectories, right? And never doing any spatial differentiation. And he picked that region because for that one, we actually had a ground truth. This was a chlorophyll map of that region, which indicated the presence of an eddy that was carrying this high concentration of chlorophyll. And when you superimpose that, that's a pretty believable boundary to that eddy. We're not saying that's the actual eddy boundary because we only used 7 floats to establish that, right? And they were not released. Only 2 of them were captured in there. But if we have this ability to process the GDP data set and make reasonably good guesses about the location of material eddies, then that's not too bad, right? So this is what I left out yesterday, and you can find more details in these papers. And I wanted to move on to today's topic, which is objective barriers to diffusive and active transport. And that will also have a motivation first for diffusive and stochastic transport. The two turn out to be very related. And then the one is transport of dynamically active vector fields, which you may not be used to, because the dynamically active quantities, which are quantities tied directly to the velocity fields, such as vorticity, momentum, and so on, we usually package those into scalar fields. We take their norm, and then we just talk about the norm of the vorticity or the momentum or the magnitude. And this is not about that. That's actually a harder problem. I don't know. That looks like a simpler problem. A harder problem. The simpler problem, which one is what? I'm going to solve the simpler problem. The simpler problem is not packaging them in these quantities into scalars, but taking them as they were originally, as vector fields. So this is about and understand the transport of those vector fields, such as vorticity, angular momentum, and linear momentum. Again, the references are, actually the first reference is incorrect because this LCS review didn't have any of this, so please forget that. But this book that's coming out this year will have all the details on it. So please forget the first reference, that's only about advective mixing. But the second one will contain this. But the notebooks that we have put out there already have the related routines for the active ones as well. So some motivation for diffusive and stochastic.
There's a question we take in the chat box. So it's from Noel Lahe that, is there some time filtering applied to the data? Example, to remove fast motions, internal waves being an example.
Oh, this referring to this,
the previous part.
Or what sorry. What is this?
I think it refers to the previous part, which the previous one, the global drifter example that you showed.
Right.
For that, was there any time filtering applied to the data to remove the fast motions?
No, the data, as I remember, was the raw data taken from as they were from the trajectories. So these were actual drifter trajectories. We didn't filter them, right? One could if they are noisy, but I think that part of it, the content of that filtering, because this is now it really pays attention to the details, right? So one could then lose some of the information. So it was not filtered. So this is the transport barriers in the lab. There's also further questions. Are they related to this? Because I see a total of three now.
No, it's the same question which you just.
Okay, thank you. So here's a motivation picture. I found this is a great video by, I don't know the person, but he goes by Drew the Science Dude. All right, and this is actually a video there, and he's illustrating the difference between diffusive and advective mixing. And he takes two identical glasses of water and puts two different kinds of dye in it. One of them is highly diffusive, that you see on the right, which means low Peckley number. The Peckley number is roughly the advective transport rate divided by diffusive transport rate. So if that is a that's a low number, excuse me, that means diffusion dominates advection. And sure enough, after some time elapses, then you see almost perfect mixing because diffusion is really at work. On the left-hand side, he was releasing dye in the exact same manner into the water, right? But it was a high Peckley number situation, which means that the advective transport dominates. So this is a weakly diffusive dye. So what emerges here, there's also some mixing going on induced by the release, okay, in both cases, but the release mechanism was the same. And in the first case, clearly these transport barriers arise, whatever they are, but we perceive them as barriers because on the one side of the surface there's dye, and on the other side, but there's barely any. There's a concentration jump. So we tend to talk about these intuitively as transport barriers, but we don't quite know what they are. So as I promised, this lecture is a bit more mathematical than I selected more mathematical topics than for yesterday. Yesterday's lectures also have variation formulations, but I gave you just the diagnostics. But here I want to formulate an actual, mathematical problem for this surface. Problem 1, find the transport barriers under small diffusion. That is to be defined what's a transport barrier, but find that transport barriers under small diffusion for this scalar advection diffusion equation. It's the classic scalar advection diffusion equation for a concentration C, which depends on space and time. And this is the total, excuse me. Well, it's not the total derivative. It's not the material derivative because that would be part of it. But this is what appears on the left-hand side, even if it's compressible. And on the right-hand side, you have then this diffusive flux that usually goes by the name of or the Laplacian. So you might not recognize this term because it's written in a more general form. What you may have seen is for the case of molecular diffusion, when it's simply some kappa times the Laplacian of C, okay? But that's for isotropic homogeneous diffusion. More generally, even in oceanography, people say the diffusion is not necessarily isotropic, not necessarily homogeneous. And the way they model that, they throw in a diffusion tensor, which is D. Okay, it turns out that has to be positive definite for it to make sense. But then the correct equation is you apply this D to the gradient of C, and then you take the divergence of it, the whole thing, and multiply by kappa. Again, if D is the identity, you just get back your Laplacian. And the context is when kappa is very small, so 1 over k is large, so the Peckley range is large. So this is the problem I want to look at. This is problem number 1. Problem number 2 is related, but it seems to arise in a different fashion. So this would be more transport barriers in nature rather than the lab. I already mentioned this database of, not just database, but movie made by NASA, which I find very inspiring. So they've taken all these whatever decades worth of flow data, and they copied the starting point in time of the flow data to the same start line, and they would let them go as if they all had been released at the same time. Now, this data set will be thinning out because obviously some of them are longer and others are shorter tracks because they were simply short in the water for short amounts of time. But when you run this data, you see some amazing barriers emerge. I mean, just look at here. These are really, after you start losing, the data, they're fairly well-defined transport barriers in this context. Now, this context, however, to your eyes, is more of a stochastic swarming, right? So you could ask, redefine or define the problem. Is that problem 2, define and find transport barriers under small uncertainty, so which would be, so the model that you would want to fit to this normally is a stochastic differential equation, which is not for a concentration anymore, but for the position of a particle, which is subject to a regular velocity field, which would be the drift term here in the stochastic differential equation, plus Brownian motion. So this is a multidimensional Wiener process, and this is the coefficient matrix of that, and the proper scaling for the diffusivity is square root k kappa here, and that's between 0 and 1. And again, the question would be, what are these barriers here? Now, is this problem on the surface? This looks completely different, but the reason why I'm handling it the same way as the other problem under the same umbrella, that it turns out to be the same problem. And that's a classic relationship between stochastic ODEs and PDEs. Namely, it's an old result, which you could just refer to it as the associated Fokker-Planck equation for the stochastic ODE. And the result is the following. If you ask the following question, how does the probability density function associated with the stochastic motion evolve in time? Namely, how does the probability density of defined, for current position X and current time T under the condition that I have started from position X naught at time T naught, how does this PDF evolve in time? It turns out that this PDF satisfies PDE. And that PDE, the right-hand side of that PDE looks very much like the advection diffusion PDE. In fact, it's identical to it, except that P is now C. And the left-hand side looks a little bit different, okay? It turns out that difference is minor, and one can fix that difference. Remember here we had the diffusion tensor applied to the gradient of P. That's not what you have here, strictly speaking. Here you have the divergence of this tensor. You have to take you take it row by row, the divergence. So you have to work on this a little bit and make some assumptions, but once you make those assumptions, which are pretty common assumptions, and they will be satisfied, you can massage this equation to the same form as the scalar PDE that I showed you before. So enough if you study that problem, and it will apply to this problem as well. I'll give you a reference to the paper where we do this in case you're not familiar with this duality. So what is then the common mathematical formulation? Once again, the advection diffusion equation for a concentration C is here, and I'm throwing in two additional terms that in applications you see sometimes. The first one is as exponential decay term, or natural self-autonomous decay, that sometimes biologists tend to throw in for species or even for some natural degradation governed by an exponential decay. You don't necessarily have to have it, but we can still do the results under this assumption, plus a source or sink term, which depends on the distribution. So actually this works in any dimension in Rn. Kappa is small, and the diffusion tensor has to be, for it to model real diffusion, has to be a symmetric and positive definite. Okay, and these are the two problems, both of which are described by this equation. Important will be, because I want to be a bit more mathematical than yesterday, to really define what we're looking for. I'm looking for a diffusion barrier, and I want it to be experimentally observable. I want it to be highlightable by tracers independently of my calculations. For that reason, I will insist that it has to be a material surface. Okay, so what's a material surface? Well, we all have sort of a notion by now what that is, but if you want to define it more rigorously, take the flow map associated with this velocity field. That's a deterministic velocity field. So it has a well-defined flow map that takes initial positions to later positions, and simply feed in an initial surface. And whatever that the deformation of that surface will be in time, this time-dependent image, that's called the material surface. So a bunch of trajectories forming a surface to begin with, and as they evolve in time material, that's called the material surface, right? This is just a bit more formal mathematically. In 2 dimensions, the surface will be just a curve, and we're tracking the evolution of that curve. So in 2D, a material surface is a material curve, okay? And here's the crux of the matter. Let's just define what we mean by a transport barrier in this context. So I would say a material barrier to diffusive transport, in words, is a material surface that inhibits transport more than its neighbors do. So that is a well-defined mathematically translatable and calculable notion, because I will make all material surfaces compete for the title of a barrier. They all will be competing with their immediate neighbors, which are their smooth deformations. And I will say that whoever prevails as the strongest inhibitor of transport will be called a barrier. Okay, so this is an extremum problem. So how do I spell out the details of that? I'll look at the simplest setting here when I have no exponential decay term in the advection diffusion equation. Forget the sources for a second as well. It all works out when you have sources and sinks, but this is easier to explain. The reference to this is this PNAS paper 2018, where you have all the details and with all the bells and whistles. So what's the transport of a scalar quantity through a material surface over T0, T1? If this was a conservative transport quantity, a passive scalar tracer, then the answer would be simple. What's the transport? Well, it's 0, okay? Because if something is, you attach a non-changing passive scalar to each and every particle, particles cannot cross material surfaces. That would mean that they would have to hit another particle and they cross them. So passive quantities don't get transported through material surfaces. Not just, I should say, non-diffusive, not just passive, non-diffusive ones, conservative scalars. But we're talking about diffusive scalars. So what's the transport of diffusive scalars through a material surface? There's very little argument about that. If you open up a book on chemical engineering or whatever, aerospace engineering, I looked at various books, geophysics, people would not disagree on that. So basically they would take this flux vector, which is kappa times the diffusivity tensor times grad C, and they would simply integrate it. If you integrate it over the surface, so just look at the first integral in here, over this moving surface, that you get the instantaneous flux of that scalar quantity through that surface. So what you do, you take the flux vector, take the dot product with the normal of the surface and integrate over the surface. That gives you the instantaneous flux over the surface. If you want transport, which is, excuse me, you want to measure the amount of stuff that got through, you also have to integrate that in time. And that's what I'm doing here. So the total transport of stuff through this moving material surface is this double integral. The first is over the moving material surface. The next one is over time. You might notice that this functional, this transport functional, is actually a function of the initial surface. Why? Because the current surface, the position of the current material surface is fully determined by its initial position. Because the flow map, remember, just advex the initial position of a surface to its current position. The flow map is deterministic in this setting. The randomness is not coming from the velocity field, it's coming from the separate diffusive part. So at the end of the day, this only depends on the initial material surface. So what we want to do, look at this functional, which is defined on initial positions of surfaces, and try to extremize it by varying those surfaces. So that's not a simple one, but it's a calculus of variations problem, which is probably more than most of us, in terms of difficulty, most of us have ever seen. Certainly it exceeded my training in calculus of variations. So I had to work on that quite a bit, but it's certainly a well-defined problem. Also, we all agree on this, right? One thing that I want to point out now and later as well is that you can disagree or agree what the definition of coherence is, and therefore there are different diagnostics for LCSs. Sometimes from the same person you get different opinions. From me, for instance, I would say, let's look at coherence in terms of stretching or rotation, or use this or use that. What if we define coherence like that? All that ambiguity is gone when you talk about diffusive transport, because on this formula, everybody would agree. Okay, it doesn't even matter which area of science you come from. So this actually has the added benefit that in the limit of zero diffusion, for which this formula will be perfectly valid because I just factor out kappa, it will give us universally defined barriers even for advection. And they will be basically the zero viscosity limit of diffusive barriers, perfectly well defined. All ambiguity is gone. All right, that's also an advantage. So this also has relevance for advective transport, basically not favoring any coherence definition over the other, just basically looking at the limit of diffusive transport, the zero diffusivity limit. So the program would be, select the most diffusion prone initial concentration. I don't want my results to depend on the initial configuration of the scalar, excuse me, partly because I typically will not know what it is, right? Say in an ocean, I will have no understanding. What I want to find the surfaces that are no matter what, are the most resilient against diffusion. So I actually want to subject all of them to the same conditions, and those will be the most diffusing prone conditions. Namely, look at this surface, and I will imagine that the diffusive scalar is initialized in a way along each and every one of them, such that its gradient is exactly normal to the surface. So if this is the surface normal, say in one direction, It doesn't actually, it could be pointing in this direction. But the point is that I'm looking at initial concentration fields that are perfectly parallel to that normal. Therefore, diffusion is very well set up to go through that surface. So I'm subjecting all these surfaces to the same initial condition, K is just sort of some multiplying factor. However, then I also want to non-dimensionalize because I don't want a surface to win this game just because they are large. Right? It's all about the quality of the permeability of the surface. I don't want a surface to be say, hey, I've blocked the diffusion the most just because I'm tiny. So not much would get through me anyway. Or I don't want somebody to win because they were not there for a long time, but only for a short time, and say, hey, there wasn't much diffusion through me because, you know, I only was there and then I stretched out. I was only there as a coherent material surface for a split second, right? So that's the advantage of non-dimensionalization. So I basically, whatever I can, I non-dimensionalize here. So I take this transport functional, divide by the time elapsed, told you why, divide by the area, told you why, and also I want to divide by the magnitude of the initial concentration too, this K, right? I don't want somebody to win just because locally there was a larger concentration gradient, right? I want a level playing field, and it's really all about the permeability of the surface under equal conditions. So this is a non-dimensionalized transport functional, which I would like to extremize. And there's quite a bit of work of mathematical work. That's the work of Florian Kogelbauer, who's an analyst, who showed this absolutely non-trivial result that when you do that, then this is the leading order approximation to this functional, plus there are higher order terms, and those are fractional powers of kappa, because there's non-differentiability hiding here. Kappa multiplies an unbounded operator. So this is not some regular power of kappa, but this is nevertheless the leading order term. So what's that leading order term? Is the quotient of two integrals. One of them is simply the area of the initial surface now. I pass to the initial surface, and then quadratic form integrated over the initial surface. And that quadratic form involves the normal of the initial surface multiplied by this transport tensor that I'll give you in a second. It turns out to be a positive definite Lagrangian quantity. So I am living up to my promise, and I'm really evaluating this integral over the initial configuration. That also means that this transport tensor will have time dependence. It will contain the current time, but otherwise I will be working over the candidate surface's initial positions that live in the initial configuration, okay? So what I want to do is extremize the leading order term. So basically, want to use the calculus of variations, multidimensional, to extremize this quantity over changes, perturbations to this M naught that I don't know yet. And wherever the variational derivative of this will be zero, those will be the locations, the M naughts, that are, at least in first approximation, stationary surfaces for this. They still then be might be minima or maxima or saddle type surfaces, but something interesting will certainly happen because the transport has a stationary value along those surfaces. But this is a multidimensional calculus of variations of problem with respect to a priori unknown surfaces. So formally, of course, I can define that problem without much technical difficulty. This is that functional that depends on those initial surfaces, and I take the variational derivative of that. If you've done variational calculus, then you know what I'm talking about. This is what's called the Gateau derivative. Basically, you have a surface that you don't yet know, and you apply a small perturbation to it, a general small perturbation to it, and then, which is, say, parameterized by a small number, epsilon. Then you take the derivative of that with respect to epsilon and set epsilon equal to 0 to find the locations where this procedure gives you an extremum surface. If you haven't done calculus of variations, then just accept that this is a generalization of the usual extremum problem in calculus, where you would be taking partial derivatives with respect to various coordinates to find the extremum of a multivariable function. But here you're taking those derivatives formally along a yet unknown manifold, and you set them equal to 0. That actually then wherever this is 0, it will give you an initial surface. Now, this problem can be solved. at some level of general, at quite some level of general, at some level of detail, I would say. And the solution is actually not complicated. It turns out to be that all these surfaces are null surfaces of a Lagrangian tensor field. And I'll tell you what the null surface of a tensor field is, but let me define the tensor field first. So this E tensor field will depend on a parameter. Those of you having done some calculus of variations, that parameter turns out to be the Lagrange multiplier associated with this problem that arises here. This is a non-standard calculus of variations problem because it involves the quotient of two integrals. You can handle that, but a Lagrangian multiplier will come in. So anyway, just think of it as a parameter. So it's a parameterized family of tensors. And it's a Lagrangian tensor that you get from our good old friend, the deformation gradient, except that now you also have to involve the diffusion tensor. Okay, so the minus transpose, inverse transpose of the deformation gradient left multiplied by the diffusion tensor, whereby you substitute the flow map in it. And then you left multiplied by the inverse of the deformation gradient. And this overbar just means spatial averaging between T0 and T, or T0 and T1, these two times, okay? Because the deformation gradient here has a running index time T in it. And if I'm interested in maximizing the transport between T0 and T1, it turns out that in the end, I have to, the solution is such that it involves temporal integration over that. And one has to then subtract, this is where this parameter comes in, parameter times the identity, okay? And this is a tensor field. Now, on the null surface of a tensor field, if it has one, is best explained here. It's a set of points such that if you connect, it's a surface, such that if you take the normals of that surface at each point and left and right multiply the tensor field with that normal, so like coming up with this quadratic form, but now imagine that E T0 is here in the place of T0 bar. So if you create a quadratic form and you left and multiply, you put in the normal of that surface into that quadratic form, and you find that along that surface, this inner product vanishes identically, then we call that a null surface for that tensor. There's a lot of null surfacing going on in general relativity, where you have Lorentzian tensors that have these. Now, positive definite tensors, as you might easily see, don't have any. So these T, which turns out to be positive definite, don't have any null surfaces, because if you feed in non-zero vectors, you will never get zero. But this minus T0 I makes this an indefinite tensor in general, and indefinite tensors have null surfaces. So the general result is, and this is valid in any dimension, calculate the deformation gradient from finite differencing as we did before, stick in here the diffusion tensor that you either know experimentally or from a model, do this averaging over, over a grid of initial conditions, and then subtract this parameterized family of identities. And this parameter, in fact, measures the strength of the diffusive transport through the surface. So if you want to find the extremizers of this principle that all have the same diffusion transport density uniformly, a given one that you give, then the null surfaces of this tensor will be those. You can then change this parameter and ask the same question again, and it gives you a different set of null surfaces. So basically, you get a bunch of these null surfaces, and this T0 will tell you how strongly they are resisting diffusion. When T0 is large, it means that they are not resisting it all that strongly, because the diffusive transport through them is nevertheless large, but they are nevertheless extremizers. So if you compare them to their immediate neighbors, they still prevail as the strongest pair, relatively speaking, okay? And this is that T-bar, this part is the T-bar that appears here. Now you see what the transport tensor is, but it's the null surfaces of this modified transport tensor that are the barriers. Now that sounds very abstract, which it is, but we were happy to be able to solve this in n dimensions. What does it say for the ocean? If we assume that the ocean is two-dimensional, it turns out you can solve explicitly for these null surfaces, and you can draw them as curves. They are now in 2 dimensions. You can draw them as curves based on the initial configuration. Those curves will be solutions of this ODE, and this ODE is drawing trajectories based on the initial configuration. So time is not ticking in this ODE. The variable with respect to, here I'm differentiating, is basically an arc length variable along the initial position of the barriers. And trajectories, this is the right-hand side of this ODE. It's actually two ODEs, and it's actually a family of ODEs depending on that parameter. And this is what it looks like. So this two-dimensional ODE, strictly speaking, a direction field, anyway, so think of it as an ODE, contains certain eigenvalues, contains that parameter. The eigenvalue is lambda1, lambda2, and xi1, xi2. Those are vectors, eigenvectors. So this formula is computable just from trajectory information. How? Are these the Cauchy-Green eigenvalues and eigenvectors? Because I denoted them with the same letters yesterday. Something very close to them. In the purely advective limit, when the diffusion tensor is identity and kappa goes to 1, they do become the Cauchy-Green eigenvalues. But they are modifications of them in the present context. Namely, these are eigenvalues and eigenvectors of a modified diffusion-weighted Cauchy-Green strain tensor, which you obtain as follows. What would be Cauchy-Green? The right Cauchy-Green strain tensor would be the transpose of the deformation gradient times the deformation gradient. That's what we saw yesterday. This is a bit more involved. It says, don't only just multiply these two, the transpose deformation gradient and the deformation gradient, but stick the inverse of the diffusion tensor in between, okay? And also put in the determinant of the diffusion tensor as a scalar. And then do the following, take the average of this in time along trajectories. If the diffusion tensor is the identity, then this is just the good old Cauchy strain tensor averaged in time. And this is a very interesting, so then it's the time averaged Cauchy-Green strain tensor, whose eigenvalues and eigenvectors are important. And this actually told us that, you know what, all those people who were basically criticizing FTLE for the longest time by saying that, oh, you're just looking at the Cauchy-Green strain tensor between this point and that point, and you're ignoring what's in between. And we said, no, we don't need that, right? It's not it. No, it would be nice to know what's happening in between. The people said, and we said, yeah, but it's irrelevant because when I'm just interested in total stretching or not, that it doesn't come in. Well, it turns out all those people were right, because if you define it in a more intrinsic way in terms of diffusion barriers, then this quantity naturally arises the time averaged Cauchy-Green strain tensor, okay? So it's the quantities associated with that, turns out the maximal eigenvalue of that or eigenvector of the time average Cauchy-Green strain tensor. If the diffusion is the identity, which is the molecular diffusion, then it's purely that. If it's a bit more involved diffusion, then you have to throw in the inverse diffusion tensor here and this D, okay? So this is a quantity from which you can calculate this ODE. That ODE lives in the initial configuration. So this is where this ODE lives at time equals T naught. You do your analysis, any trajectory of this ODE is a barrier to diffusion. Then what you can do to understand how that evolves in time, you simply apply the flow map to it and map it forward. For instance, if you're interested in closed barriers because you would like to understand vortices as regions enclosed by closed barriers of diffusion, material barriers, then what you do, you study this ODE at X naught, say look for limit cycles or look for largest limit cycles of this ODE. It can have, this is a compressible system in general, find them. And if you want to then understand their later position, then use the flow map to advect them in time. And this will be an evolving material entity, but there's a duality here. This dynamical system lives fully in the space of initial configuration. So this is not really a time, but a parameter, parameterizing that state. And then when you want to understand how this evolves, whatever you located there in time, just apply the flow map. Now, if you look at the second variation of this calculus of variations problem, because you would ask, okay, all these are extrema, all the curves of these are extrema, but which are the ones that I would really observe as outstanding, really influential ones? Then I would submit to you that it's the ones that have the following property, that they are minimizers of transport, but if you perturb them even just by the slightest amount, the transport goes up by a huge amount. So the ones that you will really observe are the ones that are sensitive to changes, because even if you move slightly off, you will see immediately large transport. Whereas if they are embedded in a family where everybody is just uniformly resisting transport, then it will not be a big deal if you make the slightest mistake in locating that surface. You're not going to see a major change in transport. So that's why one can take then the second derivative of that variational principle to find an expression that perhaps gives you a strength or a sensitivity. And that just, it's in this paper. It turns out to be very simple. It's just simply the trace of this tensor. So whatever was FTLE for advective mixing as an indicator of barriers or lack thereof, right? It turns out to be that if you modify the Cauchy-Green strain tensor by adding diffusivity and averaging in time, and you take the trace of that larger than the largest eigenvalue, that becomes your FTLE for diffusive mixing. It's an equally simple Lagrangian diagnostic, and it doesn't ignore anymore the intermediate information that we kept ignoring over the years. We only calculated this one-shot FTLE between this and that, right? Now we're calculating Cauchy-Green incrementally, and we average those Cauchy-Green strain tensors. We look at the average tensor. If there is non-trivial diffusion, non-molecular, we stick in here a non-trivial D. If it's molecular diffusion, there's just identity. So we just average the Cauchy-Green strain tensor, and we look at the eigenvalues and eigenvectors of that, okay? And the trace of it will be your, which we call DBS, field diffusion barrier sensitivity. That's the thing that will, the large values of those tell you where the influential barriers are. So this is our favorite data set, is the Aviso satellite altimetry data set, which does give you these indication of agulous rings forming at the southern tip of Africa, which we all know at this level of sketches. But if you then try to find them as transport barriers to diffusive transport, maybe the quantity that of interest to you is whatever diffusive quantity you have in mind for the ocean as important. That can be sea surface temperature or salinity or anything like that. Can we locate them from the Aviso data? And the answer would be sure. Whatever we learned yesterday, we can calculate the deformation gradient from trajectories. That's right here, okay? And then if you have some non-trivial diffusion model, just use it here. Come up with this quantity, integrate it over time, and the eigenvalues and eigenvectors of this tensor will feed into this, and just, for instance, find limit cycles of that field. Or if you just want a quick indicator, don't want to find limit cycles, just plot the DBS field, which is something like your FTLE. This is both. So in the background, you see the DBS field, which is like the FTLE of diffusive mixing. And what these nice circles here are the outermost limit cycles that Daniel found numerically for this two-dimensional ODE. So two-dimensional planar ODE. It may or may not have limit cycles, but if it does have limit cycles, it means that you have diffusive eddy boundaries. Not in all. For instance, here, if you look at the streamline pictures, they would actually suggest to you that there's also potentially some eddy there, that's a material eddy, but no, there isn't one, because there isn't. It turns out when you look for limit cycles there isn't any. But here, there is one, but none here. And these are the different values of those parameters. They also tell you how much diffusion you get through these, right? Larger values corresponding to more diffusion, smaller values, less diffusion. They all diffuse because they're not perfect barriers. Diffusion gets through them, but they are locally extrema. So they're blocking diffusion more than the neighbors. This is what Daniel Karash did as a verification of this. I asked him actually to do this, that, you know what, pick the real ones that you're predicting, and then just make fake copies of them and place them at the initial configuration and see how much they diffuse. Because one could argue that for very low values of diffusion that you see in the ocean, kappa would be 10 to the -4. That's a realistic. Actually, there won't be much of a difference, right? So maybe whatever closed material surface you pick, you won't see much of a difference. So here's kappa, and what he did here with this was what he calls a Lagrangian simulation of diffusion. So basically, he tracks these material surfaces in real life, but he only shows and updates the diffusivity or the diffusion through them based on the initial configuration. So he basically launches trajectories from these initial patches, okay? And he only initializes them. Some of these are real barriers that he obtained from this analysis. Others are fake. And he initializes this concentration to be yellow, lets the trajectories go in time. And these guys will then, many of them will stretch and fold. Other ones will keep their integrity, But you will not see that, because what he will show is that he will track the concentration along trajectories and will always update the concentration at the initial position. The reason why you would do this is that this really separates the diffusive part of the transport from any mixing and deformation that you would see for these material surfaces. So it's a smart thing to do, really just purely the diffusive part. But again, these are material surfaces that really move in time, but he only always maps them, the diffusion value, back to the initial configuration. So I leave it then to you to guess which ones were the real barriers obtained from this procedure and which ones were the fake barriers, even though, and there will be a striking difference, even though the diffusivity is 10 to the -4. So let's see that. Again, he's just updating the initial configuration, okay? That's why they're not moving. In reality, there's turbulence going on here, and you don't have to wait long, and you see a striking difference, right? So the fake ones are really eaten up by diffusion, okay? And this is only the diffusive effect separated, okay? And the ones, the real ones, this 1, 2, 3, there is leakage from them, diffusion of the concentration, but they're still preserving their integrity, and that leakage is not eating them up. They preserve their coherence even under diffusive conditions. So this is a very nice numerical verification on actual Aviso data where he was simulating this. Again, you could let them actually track them in time, and they would also deform, but when everything deforms and moves, then it's very hard to see which one is more resilient with respect to diffusion, and I thought this was a very thoughtful demonstration. This is running again, but that wasn't my intention. Same you can do for stochastic barriers, then same result holds there. The details are in this paper. And again, he did a Lagrangian simulation for the stochastic differential equation, which you can do by eliminating the drift term, and which I also learned in another context in my days in mathematical finance, where the drift term is usually much simpler than a turbulent velocity field. But basically, you take the current position and map back to the initial position under x naught. Now, if this was a purely deterministic evolution, then this will be a first integral and would not change, because the initial condition, when you associate an initial condition to a trajectory, that remains constant in time. No matter where you are in the trajectory, it's the same initial condition. But when you do this to a diffusive, a random velocity field, then no, it will change in time depending on how the randomness works, okay? And when you do this transformation, you therefore eliminate the deterministic drift, and you get a stochastic differential equation without drift. Why did he do this? Because he wanted to do a Lagrangian simulation. So rather than advecting these, eddies that he extracted with the ocean and deforming, he just wanted to isolate the stochastic transport through these curves. And again, over real ones and fake ones. And again, this is pretty spectacular if you let it run. So these are now stochastic simulations, and look, the fake ones start leaking immediately. Again, what he does, he maps these trajectories forward under the stochastic flow, which is random, and then maps them backward under the deterministic part. And this is how the same result. Now, if you know a little bit about KM theory or classical mechanics that I think I referred to yesterday, then there are these invariant elliptic curves in classical mechanics or Hamiltonian dynamics. And we always had a hard time generalizing that concept to turbulent velocity fields, because, okay, those are incompressible, so at least in that sense, they are Hamiltonian, but the time dependence is completely general and they are not near integrable. Are there still in turbulence analogs of KM curves? Here you go, even in stochastic velocity fields. These are the analogs of Kolmogorov, Arnold, Moser tori. There's a notion of constrained diffusion barriers, which are somewhat different from the ones that I have described. In this setting, I fixed the initial concentration. Remember, the initial concentration I have picked so far in a way that it would make the surface most conducive to diffusion. It was basically the surface's worst nightmare, because the gradients were aligned with each and every candidate surface so that they were normal to the surface. So diffusion had a field day, right? It's going right through. And then under those conditions, I was interested in who's resisting diffusion more and more. Now, in a real life situation, I may actually not be able to take care with the initial distribution field, the concentration field, because it's given. And I want to have the answer relative to that given initial concentration field. So instead of me tinkering with it and assuming that I don't know it anyway, there are situations in which I do need to know, and in fact, I cannot depart from that. So I prescribe the initial concentration at time equals 0, and I'm interested in what are the strongest barriers to diffusion for this particular concentration field. Again, you can solve the underlying variational problem, and it's again a two-dimensional ODE. And again, you would want to be finding, say, closed curves of that to find closed barriers to diffusion, but the ODE is slightly different. It still has a this T0 parameter in it. It still has the plus minus in it. But instead of those eigenvalues and eigenvectors there's this vector now, which is Q bar. And you have Q bar and Q bar perp, which is the rotated image. So fundamentally now this depends on Q bar. And this Q bar vector has not only that modified average diffusion weighted Cauchy-Green strain tensor, but also that multiplies the initial concentration gradient field. So this is where the initial concentration field comes in. So this is how the results will depend on that. We again have a predictive diagnostic for the most important barriers. Again, the analog of FTLE in this context would be the diffusion barrier strength would be simply the norm of this as it comes out from the calculations, simply the norm of this vector. I say predictive diagnostic. This is different from FTLE in the sense that this is predictive. FTLE basically, or PRA, they take a known setting, a known advection setting, and tell you what's most important in that setting. They basically highlight important things. Everything you've seen today is predictive in the sense that the things that I'm calculating are purely advective quantities. The Cauchy-Green strain tensor, a diffusive tensor is known. It's it's given from the model, and the whole thing is calculated along deterministic trajectories of the deterministic part of the velocity field. Yet I'm making predictions about things that I have not simulated: diffusive, PDE, or stochastic particle motion. So these diagnostics are predictive because they're saving you a lot of work having to solve a PDE and then diagnose that. Concepts like various forms of effective diffusivity and others, they are basically of the type of the FTLE. They do require you to solve the stochastic or the diffusive PDE, and then they help to visualize the important parts. But these are predictive. You never have to solve any PDE, and you never have to solve any stochastic differential equation either. These are purely deterministic diagnostics. Here's an example where you can't get around the initial concentration. You have to live with it, and that's vorticity. So vorticity in 2 dimensions satisfies a passive advection diffusion equation, although vorticity, if you think of it as an active quantity, but this is in 2D, the equation it satisfies. And the initial vorticity is just the initial curl of the velocity field, the z component of that. There's no negotiation around it. There's a thought out there that I've heard from many people that vorticity is not a passive scalar because it's not. They say, and I say, why? Well, people have shown. Well, there are papers in which people run simulations on vorticity, and they run simulations on a passive scalar field, and they get different results. But if you read those papers more closely, you will find that they get different results because they use different initial conditions for both. Of course, if you use different initial conditions for vorticity and different initial conditions for a passive scalar, you will get different results. Okay, these equations are sensitive with respect to perturbations. But if once you fix the initial condition, which you have to fix to be the initial curl of the velocity field, this is just a passive scalar equation, but it's a constrained optimization problem because I cannot tinker with that initial condition. It has to be like this. So if you solve this equation, this diffusion barrier equation, you can look for limit cycles, and this is a 2D turbulence simulation in which we have found those. And look at these red curves. Those were found as limit cycles of this equation at t equals 0. It has many of them. And then simply we're advecting them in time, right? So that they were located at the initial point, and then once you have the flow map, you can advect them in time. Importantly, they were based on diffusion considerations, and yet look how perfectly coherent they remain. So coherence is a bonus. So like I said, you could also use this for LCS calculations, and these are in fact even more resilient curves that you get from PRA or LAVD, because they pay also more attention to intermediate things. They are based on the average Cauchy green rather than the one-shot Cauchy green. This is an additional paper by lead author was Stergios, student of mine who graduated last year. He did this analysis and got, say, one of these curves. And he then also looked at the vorticity contour at t equals 0. Some of the vorticity contours were very close to that curve, but there were also other vorticity contours where he was not getting any limit cycles from that barrier equation. So he also tracked these in time. And then again, you will see a Lagrangian simulation of the diffusivity here and see when the diffusivity just goes right through these as if there was nothing there. So, but vorticity, sorry, not diffusivity. So vorticity really, initially you see a signature there, but afterwards you see not much impact on those. But look at this one and look at how over time is running here, maybe easy to see the details. The vorticity diffusion really remains circularly symmetric with respect to this. And this one really is acting as a barrier. And in terms of how they behave materially, this is how this behaves materially. And this is somebody I think asked about the Okubo-Weiss criterion. This is a contour of the Okubo-Weiss parameter, so to speak, that many would pronounce as to be a vortex. And look what happens to it when you materially advect it. In the background, the color is the vorticity, and look how this one persists. It was not constructed based from a coherence principle. It was constructed as a diffusion barrier. And yet the two go hand in hand. Somebody is an effective diffusion barrier if they don't develop small scales, right? Because diffusion loves small scales. If you start filamenting, then diffusion will cut right through. So the two go in hand in hand. This was the diffusive part. Any quick questions? I know I'm going fast, but I'm going fast. I just had more to cover. Any questions?
There isn't any. If I could just ask regarding, you alluded to this aspect of effective diffusivity. So can the effective diffusivity be inferred from these barriers that you are finding for a more complex flow field?
So the barriers, once again, we are locating without ever running a PDE simulation or ever a stochastics, purely from the deterministic flow field, right? So in that sense, it doesn't, I'm not sure how you would infer the effective diffusivity from, maybe you could. That's not something I've given a thought to. But there's various notions of not even just effective diffusivity, but others that the name skips me, that are basically helping you to diagnose and already perform simulation for a PDE and find, important locations. And I just wanted to emphasize that this is supposed to save all that work for you. So you don't need to know initial conditions, don't need to know boundary conditions, and so on. Don't have to worry about that, and still can make predictions. So that's only a 50% answer, if less, to your question. But thanks. So if I may, then I move on to active transport. Okay, this was still passive, but diffusive. So what are examples of what we would like to think of as active transport barriers? And I'd like to flash two buzzwords that you would find as related in the literature. One of them is turbulent, non-turbulent interfaces, or TNT interfaces, which are basically perceived to be surfaces dividing a turbulent region from a non-turbulent region. You'll see an example in a second. And the others that are receiving a lot of attention is uniform momentum zones, which are zones in turbulence that if you appropriately average them and do some black magic, then you basically find layers in which momentum is arguably, to some extent, is uniform. And then you could talk about the boundaries between these uniform momentum zones, which then apparently are barriers to the transport of momentum, because momentum doesn't get mixed up, right? So these are two. The first one is this turbulent, non-turbulent TNT interface is fundamentally thought of as a barrier to vorticity transport. The other one is thought of as a barrier to momentum transport at this level of heuristics. This is a paper, I think that's the very nice paper on the TNTs, and I think may have been the one that even emphasized or introduced it first, by Westerwiel, Fukushima, Peterson and Hunt from 2009, what they were doing experiments on a jet. And you see the velocity field of that jet inferred from PIV, the jet flow basically just blowing horizontally. And they were also putting dye. And they were analyzing snapshots of the dye, and they basically an algorithm to work out this jet boundary, which is basically image processing. And they would say, oh, I want a contour which sort of summarizes the dye-rich, separates the dye-rich areas from the dye-depleted areas. But then they were trying to relate that to vorticity. Is that also behaving somehow as an interface between turbulence and non-turbulence? Because there's no dye here and there's a lot of dye here, so maybe there's also a correspondence between turbulent vorticity transport or lack thereof. And when you plot the vorticity magnitude in the background, and that's what you see the color coded, there isn't really a very strong agreement. And not only that, they then pass to another frame. And if you pass to another frame, you get a different distribution. They were playing with different frames, okay? And then here he introduced then a stagnation point. There was no stagnation point here, but in the new frame, there's a stagnation point. So maybe that locally the velocity starts touching this, but then you make it worse at some other points. So the question really arises, is there a way to define objectively a barrier to the transport of vorticity, right? And then compare it with the one inferred from the dye distribution. And here's the other thing I mentioned, the uniform momentum zones. It's a very nice influential paper by Da Silva, Hutchins, and Barusik, 2014. Again, it's the turbulent simulation, not experiment, simulation, if I remember correctly, in which going through a sequence of statistical and other steps, they identified these layers in which they would argue that at least the horizontal momentum is largely constant, as evidenced by these colors. And then they had a way of defining, barriers between them. And the question is, are these then, this procedure is also heavily based on the velocity directly, so this is not objective either. You change the observer, it goes away. So is there a way to define these objectively? So then you would have to first define what you mean by a barrier to an active field. And I would not know how to do that for scalars the way they have done it, but I know how to do that for vector fields, which seems harder on the surface to find barriers to the transport of a vector field as opposed to the transport of a scalar. But it's easier for the following reason: the vector field still has directional information in it, and you have a chance to make it objective, all right? But not with scalars that have already lost any directional information. Just wanted to just very quickly give you the framework. This works for any momentum equation. It doesn't have to be Newtonian, and it can be compressible, but it has to have the general structure of some fluid momentum equation. So it all depends. The different types of fluids would have different viscous stress tensors here, but other elements are the gradient of the pressure, which is always there, and there are some external body forces, and there are some general continuum mechanics books that would have this formulation, basically practically for any fluid, but they would then make it more specific to viscous Newtonian fluids. So we can handle any of these. And the only assumption, very few assumptions, that there is an active vector field that we are interested in. That can be vorticity, linear momentum, angular momentum. And I want its evolution equation, which is here's the material derivative of that field, to be such that the right-hand side splits into a viscous part, which is really uniquely attributable to viscosity, and a non-viscous part. So I express that in this sort of heuristic way, that the non-viscous part has a vanishing derivative with respect to the viscous stress tensor, right? So it's basically everything else, okay? And I want that splitting. And my focus will be the viscous part in the evolution equation of that scale, of that active vector field. And the only assumption I'm making is that this is objective. So this part, that is the viscous part of the evolution equation for that vector field, and that can be linear momentum or vorticity or angular momentum, anything else that you want, should be objective. Namely, if I consider those general Euclidean transformations I told you about yesterday, then I should find that in the new Y frame, this term is just Q transposed times what it was in the original frame. This is the general definition of an objective vector field, an Eulerian objective vector field in continuum mechanics. Okay, so basically this is how it should transform from one frame to the other, as vectors transform between two frames. No funny business. An example of a non-objective vector field is the velocity field. It has all sorts of additional things coming in, but I'm asking this to be objective. Now, is that unrealistic? No. In fact, in all the examples that we know of, relevant vector fields is satisfied. So if you write down if you consider the linear momentum to be F, and you write down the evolution equation for F, which you can directly get from here, it's just that you have to have an equation for rho times V rather than just V, right? So if you rearrange that for F dot, which is the momentum, then the viscous term will be simply what you already have here. And by definition, or by construction, the Cauchy viscous stress tensor is always objective. That's what I told you, that people would only accept one that is objective in continuum mechanics. This contains the material properties and they have to be independent of the observer. So this is always objective. Okay, so certainly for the linear momentum, it's satisfied. It doesn't matter what kind of fluid you have. Angular momentum, this x bar is just one vector reference point with respect to which you're taking the angular momentum. Write out the equation of motion for the angular momentum or evolution equation. A little bit more complicated, but again, you can show that this term is objective. And finally, the vorticity. When you write down the evolution equation for the vorticity, that's what's called the vorticity transport equation. But you might ask, why is it so complicated? Well, because it's for completely general fluids that are non-Newtonian, compressible, and so on. Doesn't matter. The only term that only depends on the viscosity is this one, and you can show that's objective, and the rest doesn't matter. So everything we know and care about, this assumption of objectivity is satisfied, and therefore I'm comfortable, proceeding. There are some deliberations here as to what we should mean by the flux of a vector field through a material surface. And there are classic notions of vorticity flux. Doesn't turn out to be a real flux, because it's just a misnomer. For a real flux, you want flux of stuff is that stuff divided by unit time, which is the amount of stuff going through the surface per unit area, per unit time, and then you multiply it by the surface area. So even the units are not right, because you would have to have vorticity divided by time elapsed to get flux. Okay, so this is traditionally called the flux through a material, vorticity flux, but it's not really the flux in a physical sense. And it's not objective either. There's the notion of momentum flux, which you find in various different disciplines, and it's a well-accepted terminology. But I really want to insist on measuring how much stuff gets through a material surface. And when you look at it from that perspective, this flux of the linear momentum, it's actually a vectorial flux, which you get by taking the linear momentum, which is a vector, and multiplying it by the projection of the velocity on the surface normal. This is not a flux. And I know some of you are outraged, or maybe because, well, this is what I teach in fluid mechanics. No, because for it to be a flux in the usual sense, flux of anything is that the units of that thing per unit time, okay, multiplied by surface area. And it starts out good because it has momentum dimensions, but then it would have to have 1 over time. And instead of multiplying by 1 over time, you're multiplying it by length over time. That's not real flux, right? So it's okay to use it for things, and as long as you understand what this means, that's fine. But if you really want to measure things getting through in the classical sense of the word through a material surface, then it's not appropriate for that. Plus, nothing gets through a material surface, and this suggests that actually trajectories are getting through and carrying the momentum, but trajectories are not getting through a material surface, okay? So after that, we realize we need actually a physical sense of flux for vector fields that really tell you how much of that vector field gets through a surface. And it turns out to be very different. We will call it the diffusive flux of V, or viscous flux of F. And we calculate the following way. This is the active vector field, again, that can be momentum, angular momentum, or vorticity. Take its material derivative and dot that material derivative with the surface normal, then integrate over the surface, right? This has the right units, because I just told you what it's F divided by time, the units of F divided by time multiplied by surface area. And when you evaluate that this was, and I only take the viscous part of that. So this is the diffusive part. And remember, the viscous part of this was what I called HVis, and I assumed that that was objective. And that assumption makes this flux objective, independent of the observer. How do I get transport out of flux? I just simply also integrate this in time. Also, I will normalize by time. So the units are okay, it's objective. So the time normalized diffusive transport of F, and I might see diffusive here, that's the nature of it, but it's really viscosity driven, right? Diffusive in that sense, the viscosity driven active transport. So that transport functional is now this HVis, which is objective. It's the viscous term in the evolution equation of that vector field. That you integrate that over the surface dotted with the surface normal, integrate it over this moving material surface, and then take its time average. So this is basically, you can think of it either the average flux or the total transport of F through a material surface divided by the time that has elapsed. This is the quantity that, similarly to what I did for the diffusive flux, I'd like to find the extrema of this quantity. So I now have a notion of a flux for an active vector field, which is objective. This is an objective quantity, and I'm trying to find the initial material surfaces such that if I let those go under the flow and I keep measuring the flux of the vector field through those, that active vector field, then I find that these surfaces are minimizers of that flux. Okay, so same idea as in the case of diffusion, but now for active viscosity, the viscosity takes the role of diffusivity. And then we're basically done, because there's only just one result, that's actually change of variables in this integral. Again, the integral only depends on the initial surface at the end of the day. So all I do, I just reparameterize the integral with respect over, currently it's over the evolving material surface. I write it over the initial surface. And when I do that, it's an integral over the initial surface of this inner product, which, so integral over the initial surface, this is the normal of the initial surface. And that normal is dotted with what we call a Lagrangian vector field. That Lagrangian vector field depends on the initial position. It depends on the initial time. It also depends on the final time, but it's all contained in here. And this objective vector field actually is what we call the pullback of HVis multiplied by the determinant of the flow map, which is 1 for incompressible flows. And then you finally time average it. So there's 2 bits of notation here. Overbar is the time average as before. And the pullback of that vector field is the pullback that one learns in differential geometry. Basically, the pullback is a way to take a vector field, which is defined somewhere over here. And if I have a flow that's flowing in that direction, but I have no vector field defined here at the initial configuration, I can define one by pulling this one back. How do I pull it back? Well, I see trajectories until they follow until they get here. Then I take that vector along that point of the trajectory and basically transport it back here. And the way to transport it back is that I take the gradient of the flow map, which acts on vectors, and simply the inverse of that, I apply the inverse of that and write down the vector here. So this is the pullback operation in differential geometry. The reason, this is not to be fancy, to be honest, is because in each and every formula, instead of F star or F T naught T star H vis, I would have to carry this whole lengthy thing, which I don't want to do. That's the only reason. There's no other reason for that. I could not use the pullback and still write this out each and every time. But this is a handy notation, and nothing fancy behind that. So what are then perfect barriers to active transport? It's now easy to answer. So perfect barriers to active transport are barriers, material surfaces, along which this product is 0, because nothing gets through. So I will have to find initial points such that, and initial surfaces, such that when I take the dot product of the normals of those surfaces with this Lagrangian vector field, I get 0. So at each and every point of such a surface that I'm looking for, that Lagrangian vector field has to be tangent to the surface, because then it's a perfect barrier. Because the dot product of that vector with the normal of the surface must vanish. So that means that that vector field must be in the tangent space of that surface. So we in dynamical systems have another way of saying this. We say this, that such a surface must be an invariant manifold for this vector field. Because if you start on it, at each and every point, the surface will be tangent to that vector field. We say that that surface is an invariant manifold for this vector field. And that's the main result. It basically says that active barriers are structurally stable, so that the conclusion will be robust, structurally stable 2D invariant manifolds of this vector field. Or I can write down an ODE with the right-hand side being that vector field, x naught prime equals that vector field. Again, this is another example of a dual dynamical system where this variable here with respect to which I'm differentiating is not time, but we call it a barrier time. And invariant manifolds of this are initial positions of active barriers, material barriers. They will be objective. And if I want their later positions, I can just advect them under the flow map. But I can construct them fully based on the initial configuration, because I have pulled back all the information about the evolution of the surface that I needed into that initial configuration. I've processed the flow map and everything, but it's all living now at the initial configuration. So these are material Lagrangian barriers, but I can also, remember we had objective Eulerian coherent structures. I can also ask, what's the instantaneous limit of these? And those would be Eulerian objective barriers to active transport of that vector field. And all I need to do is just take this limit, T1 equals T naught 0 limit, and then I will get the instantaneous Eulerian barriers, which are invariant manifolds of the instantaneous limit of the barrier vector field, which is just at HVIS, the right-hand side of the evolution equation for the barrier vector field. So I get both instantaneous Eulerian objective barriers, which keep changing, or material evolving Lagrangian barriers to active transport. So these are, the good thing is that both of these equations are actually volume preserving. They are not your usual velocity. This involves a passage from the velocity field to other three-dimensional vector fields that are actually steady, even if the velocity field was unsteady, because I have averaged everything out here. There's no explicit dependence on time anymore. And time is, in fact, this dummy variable anyway, and you will not see that dummy variable listed here. So those are steady volume preserving vector fields, and I just need to calculate them and find their structurally stable invariant manifolds, which are 2D stable, unstable manifolds, cylinders, KM tori, for which we have LCS diagnostics. So LCSs that I discussed in the first lecture pop up unexpectedly. Basically, we have manufactured from this theory three-dimensional steady velocity field, volume preserving, in which you want to find the LCS. But these are not your original vector fields, but they are new vector fields, objective ones, associated with your problem. Now, how complicated are these vector fields? They're not that complicated. For momentum barriers, let's just look at the Eulerian one. Instead of using the velocity here and doing LCS methods on them, use the Laplacian of the velocity field. That's it. That's the barrier equation for in the Eulerian case. And this is the Lagrangian barrier equation. First, you have to pull back the Laplacian of the velocity field under F, and then time average. If you want to Lagrangian barriers, material barriers, but if you want Eulerian barriers, you simply analyze instead of the velocity field, it's Laplacian. And even from a single time slice of the velocity field, you can just run your LCS diagnostics on it forever, because the time that's sticking in this equation is not the physical time, but the barrier time. That's just a parameter that parameterizes your initial curve. You can run that forever, even though I may have just given you one time slice. And that gives you amazing resolution, even from one time slice. And finally, for vorticity barriers, you can find vorticity barriers as invariant manifolds diagnosed by LCS methods of the vorticity Laplacian. Okay, and this is a steady 3D volume preserving dynamical system, and the time on that you can run forever. So I just wanted to give, this is what it does for the ABC flow. This is a three-dimensional flow. This is the time-dependent ABC flow, which solves the Navier-Stokes equation here. Okay, not the classic one, which is steady and only solves Euler equations. The barrier equation for the ABC flow, when you take the Laplacian of the velocity field, it gives back itself plus constant. and plus here's that pullback operation. All this is just a constant here, okay? So you can run the same diagnostic that you would run on the steady ABC flow, but if you handle this as an unsteady flow and you run your LCS diagnostic, say FTLE, between 0 and 5, then this is the picture that you get. This is how much FTLE can get out of this velocity field. But if you take the same velocity data and you then run the active diagnostics on it, which means that you will be running them on this equation, which no longer has the real physical time in it, but the barrier time, which you can run for as long as you want, because it just gives you more and more detailed exploration. The more you run it, the more detail you get in the barriers. Look at how much you get from that velocity. So the same velocity, the classical analysis, active analysis, a whole lot more, right? Same for PRA. PRA can be run on this three-dimensional vector field because it's objective. If you run it on the velocity fields, which I did here, which is not, or we did here, so you're not supposed to do that because it's not objective, in fact. But the minute you run it on this velocity field, this barrier velocity field, that's objective, that's okay. And look at for how much more detail you get from the same velocity data. Let me just conclude showing you how this works, say, in a 3D channel flow. This is if you did instantaneous FTLE on a 3D channel flow, which means you take the instantaneous limit of the FTLE, which is the rate of strain. This is one time slice, apply, and you calculate the rate of strain from that, and this is the limit of the FTLE, objective Eulerian coherent structures. If you run the active FTLE on it, which basically means you take the same time slice, but now you take the Laplacian of that time slice, okay? And on that, you do an LCS diagnostic with the time frozen, and you can run it forever. And that barrier time just means you're discovering more and more, because you look at what you get from the same time slice. This is traditional passive analysis. And if you change the subject and you look for active barriers from the exact same velocity data, you get this out. Amazing. So I still find it difficult to believe. We're not using more data here, but we're beating the hell out of it just by applying LCS diagnostics to the instantaneous Lagrangian Laplacian of the velocity field and run those diagnostics on the frozen time Laplacian forever. For as long, the more detail you want it longer. And these are just, you see amazing correlation between the two structures, but as if you had an artificial way of enhancing really bad images, right? But it's the same data set. And if you look for vorticity barriers, you get even more detail, right? The only difference is that here we were calculating the rate of strain, and here we were running active LCS FTLE on this steady autonomous equation, and here on this steady autonomous equation. And this is sort of what Nick came up with, that if you do this, like two different worlds, this is the Johns Hopkins turbulence database. And if you process it instantaneously, you plot the vorticity, the levels of the vorticity. This is what you get on the left, okay? This is your best shot, this from the maximum resolution, plotted the vorticity. This would be an instantaneous non-objective assessment of Eulerian coherent structures. Instead of that, you know what? Take the Laplacian of the vorticity and run LCS diagnostics on it. He was running the TSE diagnostic, remember the single trajectory diagnostic that I told you, which you can get from single trajectories without relying on the others. And this whole new world opens up. Just look at, this is a continuation of that velocity field. And you kind of see that vorticity was getting some of it right? But all of a sudden, this new level of fantastic detail opens up. And you know exactly what these are. These are barriers to vorticity transport. I mean, actually, these were barriers to momentum transport, right? Obtained from the active TRA diagnostics, exact same data. So we're getting a whole lot more from the exact single time slice of data. And when you apply these ideas, you can come up with also a new definition, which is objective of barriers of uniform momentum zones, which basically Nick constructed here. This is an objective way of identifying the simplest, so to speak, topologically simplest barrier to momentum transport in a turbulent data set. And that's in this paper that's now coming out in JFM, but also go and find them in archive. Sorry, I think I suppose been talking too much, but thanks a lot for your attention.
Thank you, Professor Haller. We can take a few quick questions. So I'm going to read this one already in the chat box. This is regarding the ABC flow that you discussed a while back. Is there any choice for the values of the parameters A, B, and C for this?
Thanks. I didn't have, I would say it's the classical choice. The first paper that Hinon and whoever did the first paper on this, that was just a numerical exploration of the ABC flow using Poincare maps. You know, decades ago, we were using the same parameters here. And it's in this paper. If there's a classic set of parameters, then this is the classic set of parameters.
Are there any other questions? I'm going to share the email address for the meeting. So if anyone has any questions, you can email. There's one more question.
Two more, okay.
Does the active analysis of saturate as barrier time approaches infinity?
Yes, absolutely. Great question. Does, because look, if you go down here, you're using more and more time. That you would have with FTLE, by the way. If this channel flow lasted forever and we did Lagrangian analysis using FTLE, if you run it longer and longer, then you get more and more detailed structures, right? The same thing happens with the active FTLE methods. But while your classic FTLE is limited by your actual length of data, or actually you may just have velocity data for a single time slice, the active FTLE is not limited by that because it runs on the barrier time. And there, that time has a different meaning. It just means you want more scales, you want more detailed, more granular analysis of the barriers to momentum or vorticity. Okay, just keep me running, and I'll give you more and more and discover more and more. So for that reason, it does get more and more granular. So it's up to you to decide. After a while, you may not find it helpful because it's just filling up the whole space.
Are there any other questions? So the other question is from Robin Roland. For FTLE, are those added details representative of physical processes inside the flow?
For classic FTLE, yeah, for classic FTLE, right. I mean, if you just run it longer, then all of a sudden you will see the weaker hyperbolic structures as well. If you run it for a shorter time, that's the nature of FTLE. It's sensitive to separation. If you run it for shorter and there's somewhere large separation, it means very strong LCS, you will pick it up fast, right? But if there's weaker separation someplace else, then it will not prevail over the same time interval, because basically that's the trajectory is near that structure is kind of waking up, right? But if you run it longer and longer, then all of a sudden, even the weaker ones will have an opportunity to make trajectories separate. So you will stop picking those up as well, right? Now, in the active FTLE, I don't have the same meaning for the following reason, not immediately at least, because the barrier time is not physical time. So I can't say the sooner or later type argument because this is not happening in time. I think the way to explain it is that the stronger barriers that because when you calculate them with FTLE, not all of them will be perfect. So they will be kind of closer to perfect or further from perfect. The ones that are really strong will pop up first. They are strong barriers to active transport, and the ones that are somewhat weaker will start popping up later.
Okay, so in the interest of time, we will end it here. Thank you, Professor Haller, for taking on the time and
thanks a lot. My pleasure.
Lectures.